The Fukushima, Chernobyl, and 3 Mile Island disasters prove that not all nuclear meltdowns are created equal. Each was dominated by one of the 3 classes of contaminants. In Pennsylvania, small amounts of short-lived krypton and xenon gases were emitted, and so the environmental effects were basically non-existent, despite what activists may claim. In Japan, cores were destroyed but did not explode. The fuel stayed put, and so only condensed isotopes of cesium and other fission products escaped in a radioactive plume that contaminated the countryside. In Ukraine, in addition to fission products that a massive fire propelled across Europe, actual pieces of fuel, hot particles, were shot skyward and fell out within a few dozen kilometers of the power plant, owing to their size. 3 different disasters, each with their own remediation or decontamination and cleanup challenges. Challenges made that much harder by the disproportionate fear the public has for anything nuclear.
The sample that we got came from Nagoya in Japan. It's 460 kilometers from the accident site. That's about 300 miles away. The hot particle was 10 microns across. That means it is 10 1/millionths of a meter across. Obviously something you're only going to see with a powerful microscope. The particle was actually in the size range of dusts that can be inhaled and then retained in the lungs. And this is important because if you're a health physicist and you're calculating the dose that you would get from this particle, you'd have to consider that this particle might actually be trapped and result in a lifetime exposure. Think of asbestos workers who inhale an asbestos particle, and when they eventually die, for whatever reason, that asbestos particle is still in their lungs. Well, this kind of hot particle would probably do something very, very similar. The particle that we examined was a mixture of fission products from a nuclear reactor and nuclear fuels. We looked at materials like tellurium, radium-226, we saw cesium-134 and 137, cobalt-60, and a whole zoo of isotopes that probably you'll never hear about on CNN, but you'd have to be a physicist to understand. Let's put it this way. 80% by weight of this particle was made up of pure reactor core materials. So that tells me that something that came directly from the accident, directly from the core, could escape containment and travel a very, very significant distance. So it's a long distance to travel, and what happens is the particle is so very small that it will essentially travel with whatever gas it's entrained in. The winds will blow it long distances.
The critical fact here is that during a nuclear meltdown, uncooled uranium oxide reaches its melting point of many thousands of degrees. But the boiling point of the fission products that have gradually built up in the fuel is not many thousands of degrees, and so radionuclides like xenon, iodine, cesium, and strontium vaporize out of the uranium. They become gases and can escape into the environment. Xenon stays a gas and decays quickly, as happened at 3 Mile Island, and so is the least harmful escapee. Vaporized iodine, cesium, and strontium, on the other hand, will condense and become solid again once they escape the meltdown's high temperatures and then fall out as contamination. The fission products released this way in the highest amount with the longest half-life are isotopes of cesium. And so cesium-134 and 137, after they boil out of melting uranium, condense in the atmosphere and fall out to the ground as microscopic particulate, are the most dangerous fission products in terms of environmental contamination. It's mainly cesium that blankets many, many square kilometers of Japan and Ukraine. While cesium fallout links the world's worst nuclear disasters, one disaster differed in a critical way. Not only did cesium particulate make it out of Chernobyl's reactor number 4, but also the fuel that produced those fission products. That was released to the environment too, explosively. Fukushima had multiple reactor meltdowns. Reactor buildings even exploded. But the innards of the reactors themselves weren't part of those explosions. The cores weren't fully exposed, the containment buildings remained mostly intact, doing exactly what they were designed to do. Unlike modern Japanese nuclear plants, however, there was no containment building for Chernobyl's reactor 4, and so after 2 massive explosions, An estimated 6,000 kilograms of the core itself was flung outside the building and then carried thousands of meters into the atmosphere by a multi-day inferno of burning graphite. This immense eruption of steam, fire, and fuel is why contamination left Ukraine, but didn't leave Japan. Indeed, experts still don't fully agree on how large the explosions that released Chernobyl's fuel actually were, or even how they happened.
And it's a good way to diagnose which areas are going to have which types of potential health damages. The sample that we got came from Nagoya in Japan. It's 460 kilometers from the accident site. That's about 300 miles away. The hot particle was 10 microns across. That means it is 10 1/millionths of a meter across. Obviously something you're only going to see with a powerful microscope.
What we are watching is the point at which the explosion originated from. You can see the discoloration and the spacing where the steam is coming from. Look closely. We will see steam coming from that open crack. As an engineer, I know that's where that explosion came from, because that moved that entire wall there. See the steam? That was immense pressure that discolored that cover. That is the cover, the partial cover for the service pool. You can see the round side that connects to the reactor cover, the 3 plates that go over the reactor. So who would you believe? Kyle Hill, the YouTube star? Or Dr. Marco Kaltofen that found hot particles? I'm going with Kaltofen.